Hello, this is my second physics lab, and for this lab we were asked to study falling motion. And in order to do this, we were asked to record ourselves dropping an object, and the object that I chose, which is also the system that I will be studying, is a roll of duct tape, and here is the video. As you can see by the video and by the graph, this object speed is increasing over time. The reason for this is that there are forces interacting with the object that have a quantitative value, unlike our last experiment where the net force was equal to 0 and thus there was a constant velocity. And so you can see here the velocity does not remain constant since the graph of y versus t is not linear. And we did study the object's motion just over the negative y-axis, and we were allowed to do this despite the fact that the object was moving at an angle because I tilted the origin that the object started at, so it did move in a straight line across on the y-axis. And here's the data I obtained from Tracker. The main points I would like to focus on are the initial velocity and the final velocity. The initial velocity was 0 meters per second in the negative y direction, and the final velocity was 5 meters per second in the negative y direction. And this just goes to show how great the magnitude of the forces interacting on the object are, since it was able to increase the velocity by this much in not even 1 whole second. The concept that we will be studying is, again, Newton's second law, which can be shown right here for the final velocity and final position. But rather than focusing on a force that is just equal to 0, we will be focusing on two different forces with a quantitative value. The first force being the gravitational force, which is just equal to mass times the acceleration on Earth, which is negative 9.8 meters per second squared. And then the turbulent drag force, there's also viscous drag, but we'll be focusing on turbulent for this lab, is negative b, which is a constant, times the magnitude of velocity squared. And here are our models that we use to study these concepts further. Our first model just looks at the gravity aspect of the forces, and so F net is just equal to the weight force. And right here, we apply Newton's second law again, and here is our model. And as you can see, nothing other than gravity is interacting with the system. In our next code, we did include the drag force, and this is equal to negative b times the magnitude of velocity squared. And we had determined this constant b by just matching the final value that we obtained in this model to the final value, or the position value, that we obtained in our experimental data. And the F net is equal to the weight force times the drag force, and here's our model. As you can see here, there's a big arrow which is representing the gravitational force, and another arrow which is going against the gravitational force is the drag force, and thus is slowing down the object. These two models in the experimental data were compared in Excel. As you can see, both of the models fit the data quite well, but the model that includes drag force fits it better, which would make sense since there is air on Earth, and thus there will be drag force for any object falling. And so the object that doesn't include, or the model that doesn't include the drag force obviously overpredicts how far the object will fall. However, the model that includes the drag force, for some reason in the middle, underpredicts how far the object is falling. And I'm not quite sure maybe the physical reasons behind this, but I would predict that the graph of the experimental data doesn't quite match up with the graph including the drag force, just due to tracker errors / just errors in maybe the R or in the B value, or just really anything that has to do with the fact that it's reality and not a model. And after this, I also looked at the trend lines for each of the models that I made. And as you can see, the value right here is much greater, or the magnitude of that value is much greater than the magnitude for the x squared value in the experimental data trend line and the magnitude for the x squared value in the turbulent drag model. And so that is why the position is over-predicted. Now, there's questions. The first question is asking us to look at the velocity versus time rather than the position versus time and to see whether or not there will be a terminal velocity. In order to do this, I made another computer model and graphed these models in Excel. This is just looking at the gravitational force, and so it is linear because there's nothing slowing it down, so the velocity will increase forever. However, the drag force will eventually overcome the gravitational force in this model, and so eventually the velocity will no longer, or the magnitude of the velocity will no longer increase, and it will remain constant. And this is our terminal velocity. Our next question is, what if? Imagine that the object was initially thrown downward. So if it was initially thrown downward, that would mean that the initial velocity was not 0. And so in order to study this question, I made another model where the initial velocity was -2 in the y direction, and I obtained this graph. And the main question was asking whether or not the terminal velocity would be the same. And as you can see, it definitely is the same. And that I believe that is because even though you're starting at a faster velocity, this velocity is not contributing to the forces acting on the object, since something's acting on a constant, is moving at a constant velocity. Well, the force on it is equal to 0. So this will not contribute to the gravitational force or the drag force, so it's not going to contribute to the terminal velocity that results from throwing or dropping the object. And that is my lab. The end.